set, and eventually you're going to have also a model. So this model could be something like the linear model that we talked before about. It is going to get this x as the input, and then given the weights that you have, is going to give you some output, right? So I'm going to write it down in this form. So this f is the guy which is specifying my model, right? This f is conditioned to the weights, so I fix the weights, right? When I fix the weights, then x goes in and then gives you one label y, right? And that label y, what I would like to see is that it somehow looks like this label that I have in my data set, at least for the samples I have inside my data set, right? Also, I'm just ignoring the hyperparameters right now. We don't want to talk about it. We're going to talk about it later, right? We just defined it. Cool. So this is my model, and if I want to visualize it, how can I visualize it? X is a scalar, y is a scalar, so this guy is going to be some function like this, right? If I change x, given that I fix weight, this is going to just change the output, right? Everybody's cool, right? Now, what's going to happen if I change weight? The whole function is going to change, right? If I change it to some other way, then it's going to be another function, right? So this model is not essentially just one function, it's a class of functions, right? So as you change the weights, the function itself is going to change, right? And this is the whole power, the degrees of freedom that you have in your design, right? Now, what I'm going to think now, I'm going to think that my label, my true label, what I have inside my data set, is coming from a true function g. This means that there exists one function g, which is the true function. If I know it, then for any input, I can compute the output. Is it really the case? Well, it depends. Like in the projectile example we had, this was the case, right? The distance was really a function of velocity and height, right? And the thing was that we just played full, we said, like, we don't know it, right? That was the case there. But there are some other problems where we are not sure whether there exists a function. Like image classification, we don't know 100% that there is one specific function which looks at the data and tells us exactly what is the label, right? But we can always assume that function exists, right? Now, the point here is that I don't know this function, right? If I know this, I wouldn't have gone through any of that, right? Because I know the function, I don't need anything more. I don't need to do machine learning, right? So this function is not known to me, but there is no harm that I assume it exists, right? Now, if I assume that this guy exists, then let us draw it something like this, right? So this is the true function. This means that the whole thing that I want to do, I want to make my model to somehow capture this function, right? In other words, I'm going to play around with this weight. It's like tuning this weight as much as I could until I see this model is exactly catching this true function, right? Now, here comes a couple of questions. The first one is that whether I can guarantee that there exists one weight, which when I tune, then it's going to exactly lie on the function. Well, this is a big question, and this is what we're going to answer later. If you have if that model f that you have, this guy is a deep neural network, then you can say yes. This always, I mean, if you make it deep enough, then it would definitely capture the true function, right? So this is the first thing, but before we answer that, the other thing is that how I can design an algorithm which finds this optimal W star for me, right? Everybody's cool? So now the point here is that this W star is given for a function or for the case of the model, which is lying on the true function at every single point, right? This is the thing that I want. Now, what I'm going to do here, I'm going to define something called pointwise loss. And what do I mean by pointwise loss? It means that I'm going to look at one single possible input to my model. I pass it through the model. Weights are fixed, right? So I pass it through the model. I'm going to look at the outputs, right? And then for that single point, I compare the output of the model with the true label, with the output of the true function. OK? So I'm going to get x0. This is one single point, just one single point. I pass it through my model, so this is going to be y hat. We talked about it last time, so I put a hat here to just indicate this is the output of your model. This is not necessarily the true label, right? And then this y hat that you see, it might be different from the true label. But what you know is that if you would have had known this g, then the true label would have been the output of that g, right? Everybody's cool, right? OK, so I'm going to have this y0, which could be potentially different from y hat. And we talked about it last time. We can compute the difference between these two using the loss function, right? Now, one thing that I'm doing here, I'm writing it down, L, loss, computed at the single point x0, given the model parameters, right? The learnable parameters that I have inside my model. Everybody's cool? Now, why this is a function of w? Because as I change w, I'm going to change the output of my model, right? And because of that, I can potentially change the loss. Everybody's clear? OK, so this guy is a function of this weight. If I change the weight, this loss is going to change, right? OK, cool. Now, if you want to just have a bit of visualization here, this is the model that you have. And then you are just going and compute the model and the true label at one single point x0, right? At the single point x0, the model is going to give you something like y hat, and then the true label is y. And the difference between these two guys is somehow computed by the loss function, right? Now, if you change weight, that blue function could change, and that difference could also change, right? So that difference depends on your weights, right? Cool. So this is the pointwise loss, and then what we want to do, we want this point, we want the model to somehow capture the true function very accurately, right? So it means that I want this pointwise loss to be very small, right? So what can I do? I can just look at this pointwise loss and then change the weight so that this gets very small, right? It potentially just gets 0, right? But question here, is it enough that I look at one single point? No, because I can change the weight so that the function touches the true function, the model, sorry, touches the true function exactly on that point, but at other points it's totally different, right? So this is not what I want, because at the end of the day, in the future, I'm going to see new samples, right? And that sample could be something totally different from the point that I try to minimize the loss at, right? And that the output of the model could be totally different from the true label, right? So the point here is that I do not have a single point here. I have, like in our visualization, we have infinite number of points on the real axis, right? And what I want this pointwise loss to be small at every single point, right? Now, how can I do it then? Any idea? OK, so what I try to do is just in this very tiny space, and I hope that you get this. If you don't agree with me, just take it from my side, OK? The thing that I'm going to do, I am going to look at this loss, right? This is computed at one single point, right? Now, if I want the loss to be very small at every single point, one basic idea is that, OK, I'm going to sum them up, right? And then if I think this is a continuous variable, as we thought, so it's going to be integration, right? So if the loss is very small at every single point, then this integration is going to be small as well, right? If it is exactly 0 at every single point, when I integrate it, it's going to be 0, right? Everybody agrees? Yeah. But the key point here is that this x that I'm seeing is not really happening with the same chance everywhere, right? So when you have an image of a digit, right? So you do not expect to see the image full white or full black, right? It's going to be white at some pixels, black at some other pixels, right? Everybody agrees? So that means that x is not going to happen with the same chance for every single value, right? If you think about a Gaussian variable, that Gaussian variable is going to happen most of the time around the mean value, right? And it's hardly going to happen at minus and plus infinity, right? This is not going to happen. The density there is practically 0, right? So what I can say, okay, loss at every single point, I can multiply it with its density, right? And the density is telling me somehow what is the chance of that thing happening, right? It's proportional to the chance. This is the density of the variable, right? So the variable is happening around this point most of the time. So density is high. Variable is happening with no chance at this point, right? Density is 0, right? So I am going to only look at the points which have good velocity, right? So I'm going to weight the loss with their, good density. So I'm going to weight the loss with the density, and then I sum it up, right? Everybody, does it make sense to you? Yeah? Okay. Now, if it does, then what is this guy? This is? This is the risk function, yes, but do you know what mathematical operation is that? It's expectation, right? So you are taking the expectation of this pointwise loss given the distribution of your data, right? So what I can write it down in this form. So this is the expectation of the loss that you have given the distribution, on the distribution of this point. Everybody agrees? Question? So I hope it makes sense intuitively, but like if you want to talk in the Bayesian framework, this is optimal, right? The optimal thing you can do when you have a random variable, you cannot talk about a single value of it, right? You can talk about its average, right? And the best thing is that you make the average small. When you make the average losses small, this means that most of the time that you try the same model, you're going to have very small loss, right? So you cannot guarantee, this is something random, you cannot guarantee 100% of the time, right? But you want to just increase the chance. This is the reason that we do it. I hope it makes sense, but if it's a bit like abstract, you can throw it away and just take it as for granted. Like this is the right choice of the metric to just minimize in order to get the right model. Questions? Everybody's cool? OK, so let me just give you a bit of visualization here. So if this is my model, and that is the true function, then the difference between them is described somehow with this area between the two functions, right? And now, if I wanted to just simply integrate it, it means that I want to know the area here, right? So I'm going to sum the area, and I try to shrink the area. This means that the blue curve is going to touch the red curve, right? This was the idea, right? But the point here is that if I know that my data is distributed like this, so it's not going to happen here. I'm not going to ever see any x which has this value. Then why should I care about that part of the area, right? I don't care about that because there should be no x there, right? The only area that I care about is this area because this is going to be potentially the points where x's are going to happen. So I care about the curves matching somewhere around this bill, but I don't care about the curves matching too much here, right? Because at the end of the day, there would be no new x's from that area. Everybody's cool? Yeah.
So essentially, it's not necessary to use the probability distribution, but it's more efficient or simple?
Yes, but it's not only more efficient. This is going to make it feasible for us to write things down because we are going to use law of large numbers. Yeah? Yeah. If I want to integrate this loss function, I cannot, because for loss function, I need to know the true function g as well, right? I don't have access to it. Just look at the definition of this. Here. The definition is the difference between the model and true function. I don't have this guy, right? So this is going to help us just get rid of that, write that expectation with an estimator, which is now feasible to do. Yeah, just sorry, you had a question, yeah?
So you said that's optimal?
Optimal in Bayesian sense.
How can you guarantee it's a complex function?
Oh, no, not the function is convex to, like, I didn't mean that like, you can find the optimum model. I said like doing this is optimal in that sense. But then the question is whether you can minimize it. This is a big question. You can, in practice, you cannot really minimize it globally. You always do it locally. We're going to talk about it in details. But I didn't mean that. I meant that, like, if I want to design my weight, maybe I just do it this way, right? So I say I want to minimize this guy, right? Nobody can argue that this is a bad choice. This is my choice, right? So who says that minimizing this expression with respect to W is worse or better than this one? Nobody knows, right? So nobody can claim. What I said, like, if you write it in this form, then in the Bayesian sense, like if you go in the Bayesian framework and you look at everything from Bayesian point of view, then this is the optimal choice of the metric to minimize. This is the only point I wanted to say. No. Yeah, go ahead.
So what we're doing at this scene is, given the distribution we set earlier, to find out the best weight, or to minimize the risk to get the best weight. Is that?
Yes, that is. To minimize the risk, you're going to get the best weight. This is the way that you define the best weight, right?
Because I was wondering how we know the real distribution.
We don't know it. We're gonna get rid of it soon. Yeah. No worries. Questions? No question? Cool. So if you got no question, then yeah, this is the ideal form of training a model, right? So I have the risk function. This is the expected value of the loss at every single point. And then I try to minimize it with respect to the weights that I have inside my model. Then that W star is going to be the best choice of the weights for us. Okay? Now, I cannot do this. I mean, this sounds elegant, but I cannot do this. The main reason is that we don't have two major things that we need to in order to calculate that risk. The first one is the true function. I mean, if I know true function, what should I do the whole training here, right? I don't need to learn anything. I know G, so I just give X to it. It's going to give me a little label, right? So I don't know the true function. Definitely G is not known to me. Also, the data distribution is not known to me, right? Like how you can evaluate the exact distribution of cat or dog image, right? So you have this high-dimensional object. Say you have a 100 by 100 pixel image, RGB, so 3 channels. So it's going to be 30,000 different pixels, right? And then this is a 30,000 dimensional vector, right? And how you do know, I mean, even if you just take all the samples in the universe, you still cannot approximate that distribution. This is impossible, right? So the point is that we don't know the distribution, we don't know the function, how we can compute it. Now, the idea is that we can estimate it using the law of large numbers. So what does the law of large numbers says? It says that if you have a few samples of a distribution, you can average over those samples, and eventually you are going to get close to the expectation, right? That was the idea. Now, do we have samples from the true function and the data distribution? Of course we have. So if I look at my data set, every single point inside my data set is, we assume that it's coming from the true function, right? It means that if I have had this true function G, then I would give X1 to it, and then I see Y1 at this output, right? And then again, I'm going to give X2 to it, I'm going to get Y2, and so on till Xi, I'm going to get Yi, right? So I have I different samples of the data distribution. So X's are coming from data distribution. Each of them has passed through the true function, and I see the output. This is the only thing that I have inside my data set, right? So since I have those points, I can compute the loss, the point-wise loss, at those points, right? So if I want to compute the point-wise loss at particular point xi, what do I need? I need the output of my model at that point, which I can simply do, right? I give my data into my model. It's going to give me an output, right? So this is the thing that I need. The other thing is the output of the true function. Well, I have it. I have the label, right? So I'm going to replace the label there. I can compute this guy, right? This is feasible. I have the loss function, I have data, I have model, I can compute it, right? So that is not a problem. But I can only do it for the samples that I have inside my data set, right? So, but what does the law of large numbers say? It says if you compute those sample losses and then you average them, then eventually you're going to get close to the expectation, right? So assuming that those x's are coming independently from the data distribution, which is always the case. We have to assume that. We cannot avoid this assumption, okay? So if I assume that those samples are independently coming, it means that you're not going to get one cat and you take the picture from different directions. You just go in the nature and see independent cats and take the photo, right? If you do that, then law of large number, what does it say? It says that just compute the average of point-wise losses, and this is eventually a good estimator of the expectation, the risk function that you are looking for, right? So it's going to take you close to that value. So if I compute this average, so I have the loss at every single point x, and I want average it over different samples, right? I do this average. This is going to be the expectation that I wanted, right? So that expectation was the risk function, correct? And then I can get an estimator of the risk function, right? Everybody's clear? Questions? Yeah.
In practice, you usually have noise, right? So the noise
Yes.
is already inside G, or you have to consider outside?
This is a point. I mean, right now I assume that this is not like the labels that I get is completely clean, right? But if that is the case, then yes, you're going to have extra noises here. So this itself is not a good estimator. This is, again, a noisy estimator. But it doesn't matter, right? If you average them out, at the end of the day, those noises, if you assume that they are small enough, like they are small invariance enough, they are going to disappear. Yeah, but that is really the case in practice. So you have a noisy measurement. You don't have a completely accurate measurement. Yeah, that's right. Questions? No question? OK, so this guy that we are computing, which is not exactly the risk, but is a good estimator of that. This means that this is around that value, right? This is what we call it empirical risk, right? So makes sense. We compute it empirically. And empirical risk is a good estimator of the true risk. And then since we don't have the true risk, we're going to minimize this guy instead. And this is the reason that we do the training all the time in this form, right? What you do, you're going to get your data set, then you have your loss function, and you can compute this empirical risk, right? So you're going to compute the output of your model. You compute the loss between that output and the true label. You average it over all the samples that you have. This is going to give you an empirical risk, which is an estimator of the true risk function, and you try to minimize it. If you minimize this guy, then you're going to find a weight which is somehow approximately minimizing the true risk function, and this is what we want, right? Questions? No question? Yeah. Big L. Oh, this is the loss function. This is, for example, squared function or indicator or cross entropy. That small l was the output of that. Yeah. So in Python form, this is the object, right? And then that is one instant of that, right? Yeah. OK, so now we have pretty much everything from machine learning that we need to recap. So now you do know what is the main components of one machine learning approach and how you can train a model, right? So the things that you need to do, well, yeah, OK, I thought this is the last slide. So here, I mean, I just repeated everything. So this is the empirical risk minimization, and this is the training loop, the training operation that we do. But we need to somehow come up with simple algorithm for that, which we're going to do later. But at the end of the day, if I can build one algorithm which does this minimization, then the training is going to be over. So yeah, here. So if you have a machine learning problem, and right now, as I said, we are going to always focus on the supervised learning case, then we're going to have three main components. So you build your data, your model, your loss. Then you're going to use the model and the loss function to compute the empirical loss, empirical risk on the data set. And once you computed that, you're going to just minimize it. When you minimize it with respect to the weights that you have inside your model, then you would say that I have trained this model, right? And some people call it, I have seen in some texts, they call it machine learning 1, 2, 3. So these are the, a general recipe for doing any machine learning problem. So you build your main components, you just compute the empirical risk, and then you minimize that empirical risk to do the training. This sounds quite simple, but in practice, when you want to do it, every single step is going to have so many challenges. And this is what the whole course is about, right? Focusing down, by this indicate that we're always going to think about deep neural networks as the model. Why we do it, I'm going to show it today. Questions?